This video lesson is on tree diagrams, and specifically we're talking about with replacement. So a tree diagram is a way of describing probability situations. We're going to use it when there's more than one event, and sometimes it's easier than listing all of the possibilities in a sample space. So not necessarily with more than one event, but if you have a lot of options that could happen, it's easier to break it down with a tree diagram. So what we want to look at is if we have two events, say event A and event B, the options we have following this tree diagram, and just in general is, first, event A can happen. So you do this thing and event A happens. And then the second event could also happen. Another option is, first event A happens, and then not B happens. The third option would be that event A does not happen, but then event B does happen. And then lastly, event A could not happen and event B could not happen. So let's pretend that event A is you flip a coin and you get heads. So if you don't have heads, you have tails. Event B could be that we roll a dice and it's even. So if it's not even, it's odd. So I'm going to fill that on all of these parts here. So now we can see that one option is you flip your coin and you get heads, and then it's even on your dice roll. The other option is you get heads and then an odd dice. We could get tails and an even dice, or we can get tails and an odd dice. So that's what this tree diagram is really describing here. So this happens a lot when you have items that are returned or replaced. So you'll literally see something like a marble was drawn out of a bag and then replaced, and then another marble is drawn. Another option is things that don't have, like you're not removing anything. So a coin, a die, a spinner, those are just repeatedly done a couple of times, and you can't, like when you flip a heads on your coin, you don't take away the heads, right? It's still, the next time there's still heads or tails. So our example here first is Matt is having a terrible luck lately. His car is only starting 80% of the time, and his motorcycle only starts 60% of the time. So let's fill out this tree diagram. So let's start with the car first. We could say that Matt's car starts, that's option A, or event A, and not starting is not A. So these things, this first branch, we're talking about A happens, A doesn't happen. These should be mutually exclusive. They're complements of each other. It happens, it doesn't happen. And we're given this probability over here. So the percent of time that his car starts is 80% of the time. So I'm going to put that as the decimal 0.8, and that goes on the branch itself. So if his car starts 80% of the time, then the remaining time, the 20% left, is when it doesn't start. So remember the rule of complements says that event A happening plus event A not happening should total to 100%. It should be 1. So these branches should always add up to 1. The car starts, the car doesn't start, that total is 100%. All right, so we also have his motorcycle. So over here we could say the motorcycle starts or it does not start. So that's option B, event B. And we know his motorcycle starts 60% of the time, so that's 0.6. And that means using our complement rule, 1 minus 0.6 would be 40% of the time. 60% it starts, 40% it doesn't. And then down here, we're going to put the same thing. So the motorcycle can either start on time or it cannot start on time. And it's going to be the same percentages here. So really what we're saying is we're breaking down all the possibilities. The car starts and the motorcycle starts. The car starts and the motorcycle does not. Car doesn't, motorcycle does. Car doesn't, motorcycle doesn't. The point of this is that the probability of both things happening, so of following this one path here, you're going to multiply those decimals. So the probability of his car starting and his motorcycle starting is going to be 0.8 times 0.6, which is 0.48. So we could just throw that in our calculator. And then the probability of doing the car starting and the motorcycle not starting, I'm going to multiply along these branches. So 0.8 times 0.4 is going to give me 0.32. We're going to keep going following these branches. 0.2 times 0.6 would give us 0.12. And then lastly, multiplying down these branches, we're going to have 0.2 times 0.4 is 0.08. Now the beauty of tree diagrams is that the total at the end should all add up to 1 for the same reason as we have over here with our complements rule. If these are all of the options of things happening, then the total probability would be 100%. So if we added all this up, we would get 1. So now we're going to answer some questions. Part B says, use the tree diagram, got it, to determine the chance that both will start. So if both things are going to start, then we would be following along this branch here. The car starts and the motorcycle starts. So we've already determined by the multiplication that the answer to problem I is 0.48. So this decimal is a 48% chance that these things will both start. This next question says Matt can only use his car. So that would mean that his car starts and the motorcycle does not. So we don't care about the car not starting situation. That's not really helping us answer this question. His car starts, but his motorcycle does not. So that would be 32%. So 0.32 or 32%. All right, let's do this next example. So read this one to yourself. Right, so I've gone ahead and underlined and kind of color-coded the important information here. So one weird thing going on is the box is selected by tossing a coin and then randomly taking a plant. So what that tells me is that the two different events are whether we pick box A or box B, and then from there, is it a purple plant or is it a white plant? So those are our options here, and this part can be kind of tricky to figure out in this situation specifically. But if we know that we have these two boxes, you either go A or B, and then from A, you either go purple or white from B. So let's figure out some probabilities here. So in order to pick box A, it's a 50-50 chance because we are tossing a coin. So let's assume that this is 0.5 and this one's 0.5. Like A is heads, B is tails, doesn't matter. But you're flipping a coin for either of these. So they're both going to be 50%. From there, box A has 2 purple and 4 white. So that means there's going to be a 2 out of 6 chance of pulling a purple, and then a 4 out of 6 chance of pulling a white. In box B, we've got 5 purples and 1 white. So that means 5 out of 6 chance for purple and 1 out of 6 chance for white. So now we're going to multiply along each branch to find the probability of both events happening. Now we can just go ahead and use our calculator for this. So if we do 0.5 times 2/6, we'll get 1/6, and I'm going to keep filling these out. So here are all of our probabilities, and these are all in simplest form. So again, if we wanted to add all of these up, we should get in the end a total of 1, probability of 1. Our question is, the actual thing, other than just building this tree diagram, is what is the probability that it's going to have purple flowers? So we don't actually care about what happens with the white flowers. We only want to look at the probability that we would get purple. Now the probability of getting a purple by going box A purple is 1/6, box B purple is 5/12. So to find the total, we're going to add those two fractions together. So 1/6 plus 5/12, and we could use our calculator, or we could find that common denominator of 12 and add them across. So 7/12. And if you wanted to use decimals, you absolutely could here. All right, our last question here. So we've got this spinner. We want to find some probabilities. So first, let's build our tree diagram. So this one's kind of funky. We're spinning this thing twice. So that means we have 3 options for each spin. So the first spin could be pink, the next could be brown, and the other option is blue. So we could do pink, we could do brown, we could do blue. From there, we have 3 more options. So it could go pink and then pink. It could go pink and then brown, or pink and then blue. So all three of these will have the same 3 branches on the end. And this almost always happens, that you have one branch and then the second set is just the same thing repeated. That's almost always the case. So from here, let's fill out our probabilities. So the chances of getting pink, because there's 2 sets of pink and there's 4 total pieces, that's actually 1/2. So I'm going to put 2/4 just so we can see like 2 pieces of the pink spinner. For the brown, we've got a 1/4 probability, and for the blue, 1/4, because there's only one brown, there's only one blue. And then the same probabilities are going to happen after that, because we don't have to worry about replacing it, right? So we have 2/4 for pink, 1/4 for brown, 1/4 for blue. And then we multiply straight across to find the combination of both things happening. So of going pink and pink, we multiply straight across, and we get 1/4. To go pink to brown, we're going to multiply straight across, and we're going to get 1/8. And I'm just going to keep going here. All right, so we've got all of these probabilities. So now let's answer the questions. We want to find the probability that pink appears on both spins. So that would be to follow the pink and then pink track. And that's going to be 1/4. Problem B says find the probability that blue appears on both spins. So that would be going blue and then blue. So that's going to be 1/16. The last one says, find the probability that 2 different colors appear on 2 spins. There's a couple ways this could happen. We could go pink and brown, or pink and blue. So both of these could work. We could go brown and blue, or brown and pink, and brown and blue. We could go blue and pink, or blue and brown. So we've got all of these options. Really, it's everything but pink, pink, brown, brown, blue, blue. So we want to add all of these circled fractions up, and that's going to be our total answer. So when I added all of those options up, I got 5/8. So that's pretty likely, just above a 50% chance, that we would get pink, brown, pink, blue. We could go blue, pink, blue, brown, brown, pink, brown, blue, all of those options. And so this tree diagram helps us because it's really hard to look at the spinner and just say automatically the probability is going to be 5/8. So that's why we use tree diagrams.